Okay. Cominciamo? I think we can start, and sorry for the delay. First of all, I want to thank everybody to come here for this celebration. I am actually I'm now the director of IGO, but this is the history of 20 years. So, I mean, I'm just the last that take the baton after several other that contributed to this enterprise. Thanks all the people that contributed to this success. Will be very long, but I want to remember just Adalberto Giazzotto, who has been the founder, and unfortunately it's not with us, and his friend from France, Brillet. And because I think that this has been really an international enterprise, and CNRS and INFN have been had the courage of starting a scientific enterprise that at that time was really considered very difficult, and somebody talk even impossible. Now the IGO is enlarged. There is NICEF coming from joining IGO, and there are other countries that are joining this IGO, and this is becoming an increasingly international laboratory. Virgo has really changed the history of, I think there is no doubt about that. It has changed the history of how we look to the universe. It's started a new way of looking to the universe and to understand the fundamental problems that we want to solve as physicists and as a scientist. I am very proud that this is happening, this celebration, and all the laboratories here in Cascina, close to Pisa. Pisa is where Galileo Galilei was born. Is the city that has always been related to science and I mean high level of knowledge, not only in the physics, but you know I like to remember Galileo and not only the measurement of that he made on gravitation, but also the scientific method that is the most important contribution, I think, to the knowledge that we have. So I think that, again, I just might want to thank again everybody for participating, and I give now in principle to our minister, Anna Maria Bernini, would have been here, but she has been called for important outside Italy commitment at last minute, but she left to us a message, and I asked our colleague to start and see the message that she's giving to us. Thank you very much.
Good evening, everyone. I would like to greet the President of the Tuscany region, Eugenio Gianni, Nobel laureate Giorgio Parisi, the President of INFN, Antonio Zoccoli, the representatives of the Ministry of Foreign Affairs, the Diplomatic Corps, the members of the Board of Government representatives of Einstein Telescope, and all the scientific community. I would have liked to be with you in person, but I have been sent to Mexico to represent Italy at the inauguration ceremony of the new president. However, I am keen to virtually open the celebrations for the 20th anniversary of this important laboratory. First of all, I wish to remember the two founding fathers of this laboratory, the Italian Adalberto Giazzotto and the French Alain Briet. Today, it is easy to be excited about the success of gravitational waves observatories and to celebrate the emerging multi-messenger astrophysics. But at the time when Virgo was conceived, not many believed in the possibility of experimental observation of this phenomenon. The work of your colleagues, true visionaries, made possible all the scientific and technological development found by the observation, unfortunately not at Virgo, but in its twin, LIGO, of the first signal in 2015, which led to the Nobel Prize in 2017. Much more signals have since been detected thanks to Virgo, and the community has been able to obtain precise results regarding their origins. To these pioneers of science, we owe the promise to make this research thrive in the European cradle where it was born, promoting the construction of a new next generation gravitational wave observatory. To this end, Italy offers extraordinary scientific expertise, the objectively most suitable site in the heart of Sardinia, and a financial commitment of over 1 billion euros. Our country has great regard for the value of research infrastructures, which is at the heart of our G7 on science and technology, and invites Europe to consider them as the true focus around which to build research excellence. As highlighted in the recent Draghi report on competitiveness, we must avoid the dispersion of these investments and create places where researchers from Europe and around the world can conduct science together. I am thinking of virtuous examples such as CERN and the Gran Sasso laboratories. In this sense, Virgo is a highly successful model, preparing us for the next step. Virgo indeed has a crucial task of training and guiding the community during the construction and testing phase of the new infrastructure. For this reason, we hope that the interaction between EGO and the future Einstein telescope becomes ever more intense and constructive. Good work to everyone, and long live gravitational waves.
Thank you. And now I give the vote to Giuseppe Pastorelli. Please.
Thank you. Thank you very much for the invitation. I'm Giuseppe Pastorelli, and I'm heading the Directorate for Innovation and Science, the Ministry of Foreign Affairs. Would like to distinguish the President of Tuscany. The Minister was with us, Professor Parisi, and all the distinguished scientists, including Ambassador Sequi, our former Secretary General. On my way to Cascina, I was actually thinking, what are we celebrating here? It is not just another celebration. We are, first of all, here because we firmly believe in science and in the advancement of science. But we also believe that science needs international cooperation. So we cannot do it alone, not even large countries, but we can do it together. And we also here because we do know that large infrastructures are needed in order to achieve greater goals. So not only we need basic science, but we also need the infrastructure to prove what our vision is. And we're here because Europe decided at the very end, and a number of countries in Europe decided that we need to continue to be at the forefront of innovation. And in order to do that, we need to do it together. Now, listening also to the minister's speech, I guess we not only are celebrating our success, but we need to look at the future. So what's ahead of us? And ahead of us is the continuation of research on gravitational waves. And how can we do it together? Not about Italy, it's not about France, Belgium, or the Netherlands. It's about a group of like-minded countries in Europe that decided to keep Europe the forefront of innovation and technology. I guess this is the message. It's an important investment. We need to be effective. We need to know where the money of the taxpayers go. We need to look for the best possible solution to work together and to continue to give researchers and scientists the best opportunity and infrastructure in order to prove their vision. So I thank you very much for the invitation, and as Ministry of Foreign Affairs together with the Ministry of University and Research, we work together to build a stronger scientific diplomacy, because is at the very end of the day. So not only we need to discover things, but we need to share it, not only among ourselves, but also with the global south and with other countries. So that is the real essence of the scientific diplomacy. And I wish you all the success for today's celebration. Thank you.
Thank you. Now I invite President Eugenio Gianni. Please.
I'm very happy to be here for this occasion. 20 years for Virgo, and Virgo for Tuscany is an important opportunity for development of research. I think that Virgo for Tuscany, and I thank Pisa for Pisa and Cascina, where we are, is a symbol of a future in development and in research for astronomy. Io ritengo che nella città e nella regione che onorano Galileo Galilei, che onorano una ricerca e una prospettiva che vuole essere di scienza, che si applica a un'astronomia che ha sempre rappresentato in qualche modo un elemento distintivo, fin dal Rinascimento, quando noi abbiamo i corpi stellari dipinti in quelli che sono gli affreschi dei più grandi artisti, quando abbiamo il riferimento a ciò che riteneva così importante nella Divina Commedia Dante Alighieri, per quello che era il corpo delle stelle. Avere oggi un'opportunità con 280 ricercatori, 20 gruppi di ricerca, i bracci che si estendono per 3 chilometri qua nella nostra piana che ci porta qui a Cascina a vedere un incontro e un'opportunità di scambio di quelle che sono le esperienze e le ricerche a livello internazionale, rappresenta per tutti noi veramente un grande onore. E non volevo perdere, come Presidente della Regione, salutando i nostri consiglieri regionali che sono qui presenti, Antonio Mazzeo, Alessandra Nardini, salutando il magnifico rettore dell'Università di Pisa e tutte le autorità. Non volevo perdere l'occasione di dire che per noi Virgo è quello che rappresenta la storia di una regione che all'astronomia offre molto, e il futuro, soprattutto in una dimensione in cui guardare le stelle, ammirare le stelle, fin dal 33esimo canto della Divina Commedia ci porta proprio il nostro Dante Alighieri. Grazie.
City that has a history of science since Galileo Galilei and the Divine Comedy. And this thought behind the way we do science remains today in the Virgo experiment, in an international collaboration of so many institutions and so many scientists, in countries all over the world, there is a connection between the past of Tuscany and of Pisa and the present. So I am very happy as president of the region of Tuscany to be here today with my colleagues, with the rector of the University of Pisa, with Assessore Alessandra Nardini, to celebrate this day with you.
Thank you. And now I invite Professor Parisi, that he will talk about gravitational wave detection, a fantastic scientific challenge.
Okay, so thank you to everybody. Look, I have some difficult here because here the audience that is here is quite diverse. And therefore, I tried to do some talk that would be mostly understandable to people, to most of the people. And of course, these have the unwanted consequences that may be boring for other people. So, it's difficult when the audience is very diverse. Now, I think that in order to understand well this type of observatory LIGO, one had to start, and the great discovery of gravitational wave, I think that it's better to starting from far away, starting with a small amount of history, and the history of the theory of gravity. And the history of theory of gravity, I could say, but it started in Pisa. Started in Pisa with Galileo Galilei, when did, or I'm not done, not really, if we did really, or it was just a thought experiment, in which he was having two balls of different material, one relatively light, which was wood, one that was quite heavy, I think stone, and having these things fall at the same moment from the highest point of the Pisa Tower, which is quite high, and having these two things arrive at the same moment. So this was a very important experiment, and it was because it was an experiment that was showing that gravity was the same effect of different materials. That if you think of other material or something, it depends on the resistance of air and so on, but if you take a relatively heavy object, the effect is the same. Now, of course, we had done many progress after Galileo. The other progress that had been done was Newton. Newton, people say that Newton got the idea of gravity because an apple went on his head. Well, this is not clear, but my supposing that is true, I think that the things that happened was the following. Newton got the app on the hand, he looked up and he seen the moon. So he says, well, the gravity should be the same, to have the same gravity should be is the one that makes the apple fall, and that have the moon rotate around us and does not go out in the universe. So the idea was to connect the gravity that Galileo was measuring on the Earth with the gravity of the moon, and doing that, Newton discovered that the famous 1/square force was the correct one for make the relation between the gravity on the Earth and the one on the moon, and applied this thing to the room for everything. Now, the difference is the new things that happened. Of course, the theory of gravity of Newton went on for many, many years. And after the things changed by 1907. In 1907, Einstein had what he calls the greatest invention, the best thought that he had in his life, and the thought that he had in his life that gravity was some kind of illusion, and gravity was some kind of illusion because if the effect of gravity was essentially due to the fact that the space-time is not flat, and the trajectory that you've seen, like the moon that are going around around the Earth, are really straight lines in curved space. So the fact that the space is not flat, this is a fact. And essentially the idea that gravity is an illusion. Gravity is an illusion because, for example, if you stay on the space station, what you see is that you don't see, you have seen many films of Ara Samantha, that you don't see any effect of gravity. So the idea is that from their point of view, we see them to do some circle around the Earth from their point of view. They say they don't feel gravity will stay there. And okay, so this was the idea Einstein. It took 8 years for Einstein to arrive to a formulation of general gravity. And this was done only because there was a paper, the ideas of the Italian mathematician Levi Civita, which allowed him to do these things. Now, after Einstein published the paper on 1915, people started to reflect on the idea of Einstein. Of course, the first thing that happened was in the moon eclipse, in the sun eclipses of 21, people discovered that the movement of the gravity was bending the light, and the bending of the light suggested by Einstein was the exact bending that was observed experimentally. And after that, people started to study the consequences of the theory. The consequences of the theory were much more. Einstein wanted to have a theory, not that a theory that was understanding standard gravity, but people discovered that there are new consequences of the theory. And one of the two real big consequences of the theory that were discovered between the two wars were the black hole and gravitational wave. Now, what is a black hole? Well, a black hole, the idea is essentially very simple. Suppose that you stay on the Earth, you take a stone, you throw the stone up, it will fall down. However, if you throw the stone sufficiently fast, more than 11 kilometers per second, it does not fall down, it goes outside. Now, suppose that the gravity of Earth is much bigger than actually, you need them to throw away the object at a much higher velocity. And this, and of course, this becomes more and more difficult. The wave situation happens when if you throw up also the light has a maximum velocity of 300,000 kilometers per second, the gravity is so strong that also the light go back. Now, this is a situation which corresponds to a black hole. Corresponds to a black hole because also the light cannot escape from a black hole because the force of gravity is able to keep also the light inside the black hole. The other idea is essentially the idea of a gravitational wave. Now, suppose that you have what are gravitational waves? Well, the idea of wave is something that is quite common. Suppose that you take two spheres and you have these two spheres turns one around the other one in the atmosphere. The sphere compresses the atmosphere and you start to hear some sound. Suppose that the sphere moves in the water, it's clear that these spheres are going to give some wave and you get a single wave that goes far away from the spheres. If you have the same things with gravity, that you have two objects which produce gravity, you have gravitational wave that go on. And that is essentially the gravitational wave. It's something that is, the only difference is that in case of gravitational wave, what is moved is the space. Now, this was done in the 30s, but there was no idea how this thing can be proved. The technology was completely very far away from being possible approved, and also to study, and also the idea of black holes, why you should have the formation with black hole. However, in the 50s, in the 60s, the situation completely changed. You have a new telescope, you have a new studies, you discover a neutron star, and after you arrive that if you have a neutron star that is sufficiently heavy, this will collapse and will produce a necessary black hole. So there was people on one side were convinced that black hole must stay in the universe, but no one had idea how many black holes could be in the universe, or black holes could be produced, but maybe there's only a few one in the whole universe. And so people started to think of black hole, and after people started to say, well, maybe also gravitational wave, maybe we can think to measure gravitational wave. And the measure gravitational wave was something that was not easy at all, especially if you think that the thing started in the 60s with the technology of computer of the 60s that were something completely different from nowadays. The last were just born at that time. And there was Weber that started to do gravitational experiment. And this gravitational experiment was also done by the group of Amaldi in the 70s. Therefore, was a big group headed by Amaldi, in which there were Amaldi, in which they were taking a cylinder of aluminum of a few tons, 1, 2 tons, I don't remember the exact way. It was taken in a drawer, in a thermos at nearly zero temperature, and they were looking for vibration, in sudden vibration of the cylinder. Of course, that what they were doing was something that have a sensibility that was 100 less what it was, sorry, not 100, millions of times less than what is needed to see a gravitational wave. They were convinced that the result will give them negative things, but you see, if you wanted to go to Florence from Rome, you have to start to walk, to move. And it may take time, but you start to move in the right direction. And of course, Amaldi started in the 70s, and it took 50 years because people started to reflect on how improved this kind of experiment. And we had a magnificent physicist that was essentially Giazzotto, with also many other collaborators, which started to have the idea that instead to see the oscillations of a cylinder of aluminum, you have the oscillation of the space, and you look at the oscillation of the space, sending some laser light in some direction and coming back. And of course, this is something that, of course, it was not only him, it was other people in the United States and so on, but it was strongly pushed for having an experiment done here in Pisa, and also discovered something that was very important, the super attenuator, that were a crucial component of this type of experiment. So this was something Giazzotto spent all his life in doing this kind of experiment. And after the same type of movement that were happening in LIGO, in the United States, LIGO was financed, I think, in fact, at least 5 higher than the experiment in Virgo, maybe a factor of 10. So the construction of LIGO was much more simpler than the construction of Virgo here. But finally, they went in the same project, and because the point is that looking to gravitational wave from different possible observatories is something that helps because the things that you would like to know, first of all, you have the information that there is not an error that was done somewhere, but the fact that you can get the information is confirming the information. I think that the most important, having different observatories that have seen the same event, give you the information where the event comes on, where the event happened in the sky. And this was quite impressive because one of the first events that were seen by LAGO in Virgo, they were able to identify that the direction, the black hole, was a very tiny region in the sky, and people, the information was sent immediately to all observatory, the Southern Observatory, because it was on the South Hemisphere, and they looked with all telescope of the South Hemisphere looked in the right direction. We had also the radio telescope, which looked in the correct direction. And we also, the X-ray satellite that were able to see the X-ray looked to that direction. The main satellite, the most accurate, is the Beppo-Sachs, which is named this way in the name of Beppo Chialini, which was a famous physicist at the University of Florence, so another Tuscany guy. And all these telescopes went in the same direction, and they discovered how the supernova, this was a supernova, how the supernova was growing. And this is the first time that you can measure, you can see the growth of a supernova from the first few seconds, because usually people look to a supernova after the supernova became very bright, but you're losing the all initial things. So this was the beginning of something that is completely new, this multi-messenger astronomy, in which you look to the same experiment for many different things. And that was, and nowadays there are more than 100 events, black hole collisions, all these type of things that have been observed, and therefore the experiment has been a great success. Now, however, Virgo and LIGO are the first telescope that have been done, and it's clear that on the experience that have been done in this telescope is something that will be needed to construct a new telescope. Indeed, the Einstein telescope is something that will be deeply rooted on the experience that has been done on Virgo, because it's clear that in order to do something which has a more efficient of some, you needed to know how the other things worked, which were the mistakes, which were the good things. So we could not think of the project of having this new big Einstein telescope to be done in the future. And the Einstein telescope is something that is fundamental, because Virgo and LIGO can see objects which are relatively nearby to us, but we have a lot of the universe to explore. We want to understand how the old, the most ancient black hole, what the things that we would like to understand, how was space-time, what was happening in a time that was near to the Big Bang. And therefore, this can be done to go very back in the time and very long away in the time and very far away from us. This can be done only with some this type of Einstein telescope. And therefore, I'm very happy that the European community is going in the direction of Einstein telescope. And I think that it will be very important for science that one is going to take the decision to construct the Einstein telescope in the best of the possible way, in best of the possible site, because this is important, because you have to remember that the money that we get is the money of people that pay tax, and we don't have to we have to use in a proper way. So I think that it should be done the direction that this type of decision on dance and construction should be done taking the best possible place and not places that are good enough. But I'm very confident that all type of people that are doing discuss these things will eventually going to take the correct decision. Thank you so much.
Again, for these lessons that you've been able in the few time that we gave a very complete overview of what was the history of gravitational waves. Now I give the floor to Nicolas Arnaud, CNRS, INDP3, and currently I'm hosting you as Igor.
Thank you.
History of you can use this one.
Yes, and I have slides, but maybe I will take this.
Oh,
This. Thank you. So I will talk to you about Virgo more on the historical side. So that's quite difficult for me to talk in front of such a great audience, and that's even more a challenge to talk after Professor Parisi. So in order to smooth the transition, if I can go to slide number, thank you, 3, I will start with some quotes from another Physics Nobel Prize winner, Kip Thorne. So these are quotes that I found when I was doing my PhD in Virgo more than 20 years ago. So the first one, which is from 72, says that the future of gravitational wave astronomy looks bright. So that's more than 40 years before the first detections. And it's already astronomy, not just detection. So all the science that you can do with gravitational waves. Then 1983, that the quest, meaning the detection of gravitational waves, will succeed seems almost assured. So quite some confidence. The only question is when and with how much further effort. And I think that's a good way to summarize all what Virgo has done all these years. And in 95, that he was expecting that the first detection will occur in 2001 or several years thereafter. And we know now that this was more like several years thereafter. So before Virgo, as Professor Parisi said, so the gravitational waves come directly from the general relativity theory made by Albert Einstein more than a century ago. But then there were a lot of scientific discussions as to whether those gravitational waves were a real thing that we could detect, or just some mathematical artifact. So there is a famous quote from the time which says that gravitational waves propagate at the speed of thought. So you can see that it was not clear at the time that those things were really existing. But about 40 years after the gravitational waves were proposed, there was this breakthrough with this Chapel Hill conference, where a lot of brilliant scientists gathered together and agreed that yes, gravitational waves do exist and therefore are worth being searched for. So you have a quote here saying that the most important problem discussed at the conference is indeed the existence of gravitational waves. So that was 1956. So then there were basically two paths followed more or less in parallel. One was those resonant bars that Professor Parisi mentioned with the pioneering work by Joe Weber in the US. And those bars led a few decades later to a worldwide network of detectors. And you will see later that this idea of having detectors working together to look for gravitational waves is really something important for Virgo. And the other path was the interferometric detectors, that Virgo is the newest of the kind, if you want, starting in the 70s with design and the first prototypes. And the K date was 1985 at the Marcel Grossman conference, I think in Rome, where Alain Brier from CNRS and Adalberto Giazzotto met. And so they started together what will become Virgo later. So this picture shows you Alain Brié on the left and Adalberto Giazzotto on the right. So Alain Brié is a laser specialist. So he brought all his knowledge about laser and how to make precise measurements. And Adalberto Giazzotto was already an expert in seismic isolation for those first gravitational wave detectors called the resonant bars. And he also had ideas that some sources should be searched for, and therefore the instrument should have properties particular. So altogether, they had complementary expertise with a common goal detecting gravitational waves. So then Virgo started. Here you have the cover of the initial proposal, which is still in Italian with contributions from Pisa, Napoli, Rome, Salerno, and Paris in France. 2 years later, you move to the concrete proposal of the Virgo experiment in English this time. So some quotes. The first goal of the Virgo project is to succeed in detecting gravitational waves. One expects to observe at least a few events per year. Then you have something that would still read very well today, which is that the discovery of gravitational waves will be a major event in the history of physics, and yes, it was. And it will open a new era in the observation and understanding of the universe. That's what we are doing now. And you also see that there is this long-term goal of being one component of the gravitational wave detector network, which will involve other detectors in other countries and provide data of astrophysical interest. Clearly, those goals imply a collaboration with other groups having similar projects, and that's exactly what we are doing now. So why the name of Virgo? If you look at the cover of this 1989 proposal, it's clear. It's named after the Virgo cluster, which contains more than 1,000 of galaxies, which is quite far in the universe. And if you have a lot of galaxies, you have a lot of stars, so you have a lot of potential sources of gravitational waves. And so the idea will be that the Virgo detector should be able to detect sources until that cluster of galaxies and possibly beyond. And that's also something that has been achieved at the end. So the site, obviously, we are here in Cascina in Tuscany, a very good place, a good idea to put such a detector in a fine part of Italy. So here you have documents showing the discussion of the town city council in May 89 about the gravitational wave detectors Virgo. So the town council notes that this is a project of high scientific interest, which will be built in Cascina and more precisely in San Stefano a Macerata. And it seems that they got an unanimous vote, which is very good, and giving some ratings for the experiment. So that's what the site was looking like before the construction, and that's what it is now seen from the sky with those 2 3-kilometer long arms. So here we are at EGO, which is the European Gravitational Observatory, so the structure which hosts Virgo, which was founded more than 20 years ago by France and Italy. And now the Netherlands have joined as well in March 2022. And you can see a picture of that event. With the Zoom screen behind, you see that it was during the pandemic time. But I like that picture very much because you see people together and you don't necessarily understand whose hands are there, but that's a way scientific collaboration should work. And so EGO has several missions, including the functioning of the Virgo detector. So this is a timeline that we had prepared for the first detections of gravitational waves with Virgo. I'm not going through all of this, but so the construction started in 1996, ended in 2003. Then there were some first part of data taking and another program. So Virgo showed that a detector like this could work and could achieve the sensitivity it was expected to reach, but people knew that it was not enough to detect gravitational waves, probably. So they already anticipated a second generation detector that we called Advanced Virgo, which took about 10 years between the initial design and the actual detections of gravitational waves. But the idea was to make a new detector more sensitive this time hopefully to reach to probe enough universe to see gravitational waves. So an important part is this idea of a network. So this slide and the next one will tell you more about this. So we have these things that we call MOU, Memorandum of Understanding between collaborations. And this is the one which was signed in May 2007 between Virgo in Europe and the LIGO collaborations in the US, which basically says that it's to establish and define a collaborative relationship between Virgo and LIGO, to lay the groundwork for decades of worldwide collaboration in a spirit of teamwork, and with the idea that new partners could join later, which was the case because in October 2019, the Japanese-based KAGRA detector joined, and that's why you will hear a lot this LIGO Virgo KAGRA or LVK acronym to talk about this meta collaboration. And so the idea is that on this scheme, you have on the one hand the interferometers, the detectors which are producing the data, and on the other hand, what we call the catalog, which is all our results and all the science we can extract from our detections. So the first part is done detector by detector, but once you cross this red line more or less and that you start analyzing the data, this is all done jointly by LIGO, Virgo, and KAGRA together. And so that's what the network of interferometer looks like today. In yellow, you have all the detectors taking data, with Virgo obviously here, the two LIGO detectors in the US, and KAGRA under the Kamioka Mountain in Japan. And soon in the future, you may get LIGO India. And you have in Germany Geo 600, which is an extremely good R&D facility that we use to test a lot of technologies. So why working in a network? Because the real gravitational waves coming from far away in the cosmos should be visible in all those detectors. So with a network, you gain confidence for gravitational wave detections. You reject fake signals, fake noise coming from a given place. And you also are able to localize where the sources of those signals are in the sky and to measure their parameter. So let's move to the detections. So the first one was on September 14, 2015. So that was a Monday. And I think a lot of us remember what we were doing at that time. So you know that the Virgo detector was off at the time, so the data only came from the LIGO detector. But I told you that Virgo is contributing to this network with also its scientists analyzing the data. And in fact, the first information about this event came from a Virgo scientist, Marco Drago, sending an email saying that there was a very interesting event in the last hour. And that very interesting event was the first ever detection of gravitational waves. So that was on September. The announcement was on February 11, 2016, simultaneously in various places. And here you are pictures of the announcement in this room with various Virgo and Ego people. And in the meantime, you had 5 months of hard work to analyze all the data and making sure that that signal was indeed a real detection. 2 years later, with the advanced Virgo, we had on August 14, 2017, the first real signal seen not only by the two LIGO, but also by Virgo. So that was the first ever pre-detector detection of a gravitational wave signal. On the right-hand side, you can see some infographics that we produce each time we have a result important to share with the world. So we are not just only building detectors, analyzing their data. We have a lot of effort to do outreach and education. So that's an example. We produce a lot of resources like that, and we make sure they are translated in all the languages of the LIGO Virgo KAGRA collaboration. So 3 days later, August 17, 2017, this fantastic August 2017 month, we had the first ever observation of the fusion of two neutron stars. And thanks to the capability of the LIGO Virgo network to pinpoint the location of the source in the sky, the source of that signal was found by optical detectors. That's this little spot that you see near let's say, a random galaxy in the sky. And that led to the birth of multi-messenger astronomy with gravitational waves. So these were the first detections. Then we took confidence and we were able to take data for a full year, April 2019 to March 2020, sorry, not 2027. So almost a year of data taking, which means more than 250 days of data accumulated. And the result of this can be seen on this plot, where you have basically the number of days of observation on the horizontal axis, and on the vertical one, the number of events actually detected. And you can see that the slope of the curves, that is the rate at which you detect events, really changes a lot. And that's due to the improvements in the sensitivity of the detector of the network. So in 1 year, we moved from like 10 detections to 90. So we almost multiplied by 10 the number of detections we had. So to celebrate all this, in 2021, IEEE, which is the Institute of Electrical and Electronics Engineers, awarded some milestone to the 2 LIGO detectors and to Virgo. So if you visit the site later, you will see displayed on your way to the central building. So as a conclusion, the Virgo project was designed maybe 35 years ago, and the experiment is more than 20 years old now. And that was an European-based project, which I think is important. And I think it's fair to say that we have fulfilled some of the goals that the founding fathers of Virgo had envisioned when they started working on the project. And you have to remember that detecting gravitational waves had always been considered as extremely challenging, and we managed to do it. So Virgo contributed to the first detection of gravitational waves, and Virgo is now contributing to more detections and to the study of those waves and of the sources that produce them, both as a detector and as a collaboration of hundreds of scientists in this LIGO Virgo CAGRA global collaborations. So that already all those achievements made Virgo part of the scientific history, but I think we are not ready to become history yet, and we still have a long scientific and active life ahead of us. So I told you about history, and I think the story of Virgo will be continued in the talk by Professor Jeme just after mine. Thank you.
Thank you. Thank you for your talk. Excellent. Thank you very much. Now, Gianluca Gemme, who is the spokesperson of the Virgo collaboration. More than 800 people.
Thank you. It's really an honor to be here in front of such distinguished guests. It's an honor to host you in this beautiful site, the European Gravitational Observatory, which hosts the Virgo detector, which is this huge scientific infrastructure, which I hope we will be able to visit after my talk. Let me spend a couple of words about the Virgo collaboration, the people who actually runs, designs, operates, improves this detector, these beautiful instruments. As you can see, the Virgo collaboration is mostly based in Europe, many European countries. We also have institutions coming from other areas of the globe. We recently admitted one new group, mostly based in Brazil, so we are going really international. Today, Virgo is made by more than 900 members, 160 scientific institutions in 20 countries. And the photograph at the bottom of this slide is a very beautiful photo, if I'm not wrong, taken in 2017 after the detection of the binary neutron star, the announcement for the detection of the binary neutron star. At that time, the collaboration was smaller. We were about a couple of hundred people. after that detection, after that announcement, the collaboration started growing, and now we are more than 900. As Nicola already said, we are not alone. We are part of an international network of gravitational detectors of gravitational waves. 2 detectors are based in the United States, the 2 LIGO detectors. One is in the northwest of the United States in Washington State. The other one is in the southeast in Louisiana, Livingston. Virgo in Europe, and our Japanese colleagues of Kagra in Japan. A new detector is being built in these days in India, a 3rd LIGO detector, which is expected to come online around the end of this decade. The worldwide community that operates these detectors is made by more than 3,000 members over 4 continents. So it is really a worldwide, global scientific community. This is a snapshot which shows you the various observing runs. The colored boxes show you the periods during which LIGO, Virgo, and Kagra were taking data starting from the first observing run between 2015, where, as you can see, only LIGO was online, and then the other observing runs in the next years. The period between the observing runs are typically periods that we use to improve, upgrade, try to make our detectors better. Today, we are there. We are running the 4th observing run, 04. As you can see, the 2 LIGO detectors and Virgo are taking data together. They're actually taking data now while we are speaking. Virgo is observing, the 2 LIGO detectors are observing. It is possible that a gravitational wave hits the detectors and we get a message on our cell phones while we are speaking. Kagra is not taking data with us yet. It is expected to join the run in the first months of the next year. Kagra is actually recovering from the very bad earthquake that hit Japan at the beginning of this year, and which caused serious damage to the scientific infrastructure. So we are really waiting for our Japanese colleague to join us in this scientific run. These 2 pie charts show you how Virgo is behaving in this scientific run. The green area in this chart shows you the fraction of time that Virgo is actually taking data, which is about 3/4 of the time, which is an excellent number. These are very complex and delicate machines. Being able to actually take scientific data for 3/4 of time is a major achievement. And Virgo, by the way, is the best detector in the network from this point of view, from the point of view of reliability and stability. As far as the network is concerned, we can see that we are able to run with the 3 detectors online for about 1/3 of the time. For approximately 90% of the time, we have at least 1 detector taking data. And I will tell you soon why it is very important to have 3 detectors online at the same time. These are the sources of gravitational waves that we detected so far. This is a cartoon, obviously, which tries to represent a binary system of 2 black holes. Black holes are not black balls like this, but this is just to give you an idea and to give you an idea of the gravitational wave emitted by this kind of system. All the sources of gravitational waves that we detected so far are of this type, a binary system made of 2 compact objects spinning around one another and emitting gravitational wave in this process. The vast majority of signals that we detected is exactly of this type, so 2 black holes. In some cases, one of the 2 objects is a neutron star. In very rare cases, only 2 cases so far. The 2 objects are made by 2 neutron stars. The first one was the event which was described by Nicolas in 2017. A second one happened during 03. This is the same picture that Nicolas showed a few moments ago. It shows the total number of events detected by the network starting from 2015 up to the day before yesterday. As you can see, we detected more than 200 gravitational wave events in total. 61 were detected during the first part of the current run, and the other are being detected in these days. As you can see, this curve is made of several pieces, and it's clear that at this point, around this point, there is a sudden change of slope. The curves become much more steep, and this is basically linked to the increase of sensitivity of detectors. So the rate at which we detect events depends on how sensitive are the detectors. Best sensitivity, more detections for the same time. So it's incredible because if you think about it, 10 years ago, we were still waiting for the first detection of gravitational waves. Now we detected more than 230 events. Gravitational wave detection is becoming a routinary task, almost boring. I mean, when we get a message on our cell phones, no, you don't have to say that. Okay, I know. When we get a message on our cell phones, oh, another binary black hole, okay. No big deal. We are waiting for another BNS. The rate at which we are detecting events is approximately one event every 3 days, so more than 2 events per week. We have a very complex and sophisticated system to inform the astronomical and astrophysical community about our detections. As soon as we detect an event, we send a message out to the external scientific community to inform them that we detected the event, and we give them the basic characteristic of the event, the possible source, the time of the event, and also the sky localization. This is very useful because the idea is that gravitational waves are one of the messengers we use to study a source. It's very interesting and very good to study the source using also other messengers. So when we detect an event, we spread the news across the internet. Astronomers get the notification, and they can point their telescope in the direction of the event and try to follow up the event, looking for other kinds of emissions. And this actually happened in a spectacular way in 2017. How Virgo contributes to the network? Well, this is linked to the importance of having 3 detectors looking at the same time to gravitational wave events. This picture shows the localization in the sky of one event detected a few weeks ago, based only on the data of the 2 LIGO detectors. If we fold in the Virgo detector, this is the localization that you can get. So using 3 detectors, you can localize the same event. This is the very same event, going from hundreds of square degrees in the sky, which is making it basically impossible to localize the event for the telescopes, to few degrees, which effectively enables multi-messenger astronomy. So Virgo is effectively enabling multi-messenger astronomy in the network. We, together with our LIGO and CAGRA colleagues, are committed to the principles of open science. All our scientific data are published, so are available to the wider scientific community and to the public, to everybody, actually, few months after they're taken. We keep the data proprietary. I've never been able to say this word. For 1 year and a half, this is the time that we need to finalize all our analysis, and then we publish them, and everybody is free to get our data, look in them, analyze them as they want. And I think this is a very important initiative of our collaboration. This site is an open site, Everybody can log in, get the data, get documentation, information about the detectors, tutorials, software, etc. What's next? Well, next is the next observing run, which according to the current plans is going to start sometimes between 2027 and 2028. The goal is to improve the sensitivity of the detectors by a factor of approximately 1.5, improving several aspects of the technology that enables our science. We have also plans for the longer term, for the next decade, and the name that we are giving to this conceptual study, which already began a couple of years ago, for the improvement of Virgo in the next decade is Virgo Next. And Virgo Next, in our vision, is the ultimate detector that will be hosted in the current infrastructure before third generation, before Einstein telescope comes online. The installation of Virgo Next is expected around 2030. It will be a detector hosted in the current infrastructure and based on the same basic technology as the current detector. Virgo Next will push the design as far as we believe is feasible in this current infrastructure. And Virgo Next, and this is a very important message, will guarantee continuity to gravitational wave science in Europe across the next decade. Virgo Next will be not only a major scientific project, which we deliver excellent science, it is also a step toward third generation, a step toward Einstein telescope. ET was the pioneer of the idea of the third generation gravitational wave observatory, longer baseline, longer arms, new facilities, innovative technologies. Virgo Next core technology is essentially the same as the technology that will be used in the ET-HF high-frequency interferometer. Large power circulating in the arms, squeezing fused silica heavy masses. From the Einstein telescope perspective, Virgo Next will be a pathfinder for ET and will greatly reduce the risk of not achieving design parameters. You can see this is the same concept in numbers. If you look at the parameters of the current detectors, at the parameters foreseen for Virgo Next, and at the design parameters for ET-HF, you will see that there is a bridge between the current generation of detectors and the third generation, and Virgo Next is supposed to fill this gap. Oops. Sorry. One back. Okay. Takeaway messages. Virgo is delivering and will continue to deliver great science into the next decade. Virgo, together with LIGO, was able to answer few questions. There are still a lot of open questions and still few answers. Physics of neutron stars, continuous waves from pulsars, stochastic background, cosmology, all open questions that the Virgo detector, together with LIGO, will try to answer in the coming years. Virgo Next is the gravitational wave science in Europe across the next decade, and also a pathfinder for ET. There are many lessons and ideas for improvement that will come from current detectors that will enable third generation. Also, non-negligible aspect, these detectors, the current detector, will guarantee continuity for early career scientists who are those who will be running third generation. Thanks.
Now the final part of this evening, I will give the floor to the three funding agencies that have. The first one is Vincent Poirot, CNRS Deputy Director. Please.
Hello to everyone. So it's my pleasure to be here for this 20th anniversary of Virgo. So I am a scientific director at NTP3 in charge of astroparticle and cosmology. So NTP3 and CNRS, and I also represent Antoine Petit, the director of CNRS, and Christelle Roy, the director of INTP3. So Christelle Roy is sorry, she cannot make it today, but yeah, she's very sorry to not to be there today. I'm also the president of the EGO Council. So we heard that Virgo is truly a collective effort by many countries. It started with INFN and CNRS with a strong partnership. And now we have many more countries in the game. So we had Netherlands, Spain, Belgium, Poland, etc., etc. So it's really a collective effort. And I remember some conversations in the cafeteria more than 10 years ago, and many people were convinced that it was not possible to find gravitational waves with Virgo. These people were wrong, because as we saw, we already discovered 230 events since 2015. So this is really something incredible. So Virgo just opened a new window in the universe. It's like you put new glasses in front of your eyes and you see the universe with other eyes. You see with other messengers. Of course, there were some difficulties during these 20 past years, but for sure, Virgo is a terrible success, incredible success with outstanding results. We heard about this gravitational wave events with the neutron star binaries, which completely revolutionized the way we see the universe. The success of Virgo is built on EGO, on the EGO site, with more than 60 people working here, and also is built on the labs, international labs that are built and is running these interferometers. So we saw that Virgo is very important in this network with LIGO and CAGRA. You see the localization is really improved when you put all these interferometers. So and the proof of the success of Virgo is that the fact that the collaboration more than tripled since a few years. So you see the number of people in Virgo, it was much less a few years ago. So it's really a sign of the success of Virgo. And now we talk about the past, I want to talk about the future. So Gianluca already talked a bit about this future. There are some people here for a board of Einstein Telescope. So I assume that the start of Einstein Telescope is in 2040 or so. So it means that we have still more than 15 years to go for Virgo. So there is a lot of room for Virgo. This is why we discussed about this, the future, these upgrades of Virgo. And for me, there's a bright future for Virgo and here at EGO. There will be many changes in these coming years. Of course, we discussed about the upgrade. So we'll have to upgrade the interferometers for O5. We'll have also to upgrade the detectors for Virgo Next. There is also this big change about the collaboration. Now, the Virgo collaboration will become an EGWIN collaboration with Virgo, LIGO, and CAGRA. So it's a big change to come. And I said it was a collective effort. It will be now a world collective effort. And it will be something, of course, very important. Big change. And for me, the success of Virgo is an essential step for the future of gravitational waves in Europe for Einstein Telescope. So Virgo will be the base where we can build the success of Einstein Telescope. And as Gianluca said, this will be the place here where we can push the technologies, or we can test the technologies for Einstein Telescope, especially for the high frequency Einstein Telescope. So thank you very much.
Thank you, Vincent. Now, Stan, about the NICEF director.
Yeah, thank you, Massimo. And ladies and gentlemen, it's for me a big honor to stand here, close to what I think in the heart of Italy, one of the most sensitive instruments ever built. And it is thanks to the very bold ambitions of INFN and CNRS 20 years ago that you made the decision to go for this instrument, and I'm very grateful to that. I'm a director of NICEF, and I feel very privileged in the last few years, because not only were we heavily involved in the discovery of the Higgs boson in 2012, but one of the surprising and for me life-changing events almost was when Jo van der Brand came to my office in 2015, showing the very first signals of the very first observation of gravitational waves that have just been presented to you by the excellent speakers before me. And I hope that you allow me to give a few words on the Dutch angle of this story. So, you know, we started to join this endeavor 15 years ago, I think from 2009 or so. So that was later, much later than CNRS and INFN has pursued this. And in 2022, we became full member of EGO. And I think there is even a Dutch flag here visible. I like to believe that NIC have made significant and sometimes essential contributions to the infrastructure. And for example, during the time of the very first neutron star merger observation, actually the spokesperson of the collaboration was a Dutchman. So I don't say anything new, but maybe I like to articulate 3 points. And that is that I think we should take the bold initiative that CNRS and INFN has shown 20 years ago now to go into the endeavor of the Einstein telescope, a magnificent dream. And we have to collaborate with many countries to make it realize. I think all of us share the same dream of the Einstein telescope, of creating the 3rd generation infrastructure. And we may have different views on how to realize it, but we talked about it this afternoon quite extensively. But in a way, I think that these can be used to strengthen the unique and complex Einstein telescope cases. The second point is also made by Vincent and others before. Virgo is a European lab where the scientific measurements will continue to be made for the coming 15 years at least. So the future of Virgo and of the Einstein telescope are very intimately linked to each other. And we need a global European vision that includes both the Einstein telescope and Virgo. And processes are ongoing to do so, and also to improve the organization of Virgo. We heard also that before. And NICEF and the Netherlands continue to support Virgo in the coming years. The third thing is that the technical and scientific challenges for Virgo and the Einstein telescope are really monumental. And I think we really benefit from an open and inclusive community. And so we have to inspire the young generations, the generations after us, to step in and to take over. But not only people, we also should cherish the diversity in instrumentation and in the environment. So again, talking about the Dutch perspective, I think that, for example, we should embrace the ET Pathfinder, which is currently being constructed in Maastricht, and the Crystal in Liège as opportunities that should be embraced and be part of this network to solve technical issues that Einstein telescope will be facing, in particular, for example, this low frequency cryogenic stuff. So I think that we need to do that in order to guarantee a lively and creative exchange of ideas. At the same time, I was with Antonio only 2 days ago in the Big Science Business Forum in Trieste. We saw a lot of interest from industry, and we should also connect to the industry and make them sure that they see the challenges that the future Virgo and Einstein telescope is posing us. So with that, I'd like to thank again the organization for this event, and congratulations for the 20th birthday.
Thank you for your presentation. Thank you very much, Stan. And last is Antonio Zoccoli, INFN President. Thank you.
Thank you, Massimo. It's an honor to be here. This week is a second celebration in which I participate because on Tuesday we were at CERN for the 70th anniversary of CERN. Now we are here for the 20th anniversary of Virgo. And these are both very important scientific enterprises with very big success on science. And here I would like, first of all, to thank all the researchers, all the technicians, all the people that made it possible. Since the beginning, it's a good history for science. We started in the end of 80s, and it was understood a few years before, in the 70s, that it was possible to discover, to discover gravitational waves. The scientific community started to look for it, but the technology used was not enough, was not good enough. And then, as usually when you want to discover something, you need to make a step forward and to change the technology. And this happened in 1989 when Alain Brillet and Adalberto Giaddotto joined. They had a new idea, and both of them kept their own knowledge. One on the laser, one on the suspension, mechanical suspension. And after a long endeavor, they were able to build up a new infrastructure from greenfield, make it to running, to improve during the years the sensitivity, to pass through some crisis because maybe you don't reach the performance you would like to reach. Maybe you think that you are able to detect gravitational waves, but you don't detect them. But at the end, you still continue to believe. And at the end, you do it and you discover it. And then this happened in 2015. And then you start to open a window to investigate the universe. 2 years later, you are able to detect the gravitational wave together with the electromagnetic partner, and really to show that it's possible to have a multi-messenger physics. Clearly, this was an important step, but it just opened a little crack, not a window. We have still to enlarge the window, you enlarge the crack, and to be able to detect many more events and to understand much more in deep the secret of the universe. So this brings me now to the future. So we are here, we have still a future for Virgo. There will be next run, we have to improve the detector. There will be Virgo next, and in parallel is starting the effort to build up a new gravitational wave infrastructure, Einstein telescope, and start again from a greenfield. We know that we have to change the technologies, we have to go underground, we have to make very strong improvement in all the infrastructure in order to be able to go much far, much closer to the origin of the universe, to study the fundamental law of the universe, the secret of the universe. So I think that we have to learn the lesson we had here, the fact that we can reach these goals if you work together, not in competition, putting at disposal all the knowledge you have, and try to be convincing, to be convinced yourself that this is the best solution you have, and to convince all the rest of the community and the politicians that this is an important endeavor. And I think that we are on the right way. Of course, as usually when you start a new enterprise, We have different point of view. We have many discussion, and at the end, if you are a good scientific community, you will be able to find the best way to reach this scientific goal. So I think that Virgo must be a pivot in this new enterprise, must play a role, because only here we are able to detect the gravitational waves, and we are able to prove the new technologies. And clearly, as I told you before, we don't have to make it in competition. I think that if you want to build up something new, you have to build up a network of laboratory where you share your experience in Italy, in Japan, in US, in Netherlands, in the rest of Europe. You have to share all the knowledge you have, and you have to find the best scientific solution. I think that at the end, we have a clear way to pursue, is science. If you wanted to build up a new infrastructure, we have to follow the best scientific option for this infrastructure, the best technology which is needed to fulfill this goal, and to reach this goal, and to achieve and build up a new infrastructure. So I think that we have to look forward. We have to keep in mind that Virgo and EGO and Einstein telescope are in some way the same research. One is following the other one. So they are not two different things, two separated things. One collaboration working in Virgo, another collaboration works in Einstein's telescope. I think this will not work. And if we want to be successful, we have to work together, as usual, as we did in the past, as we did at CERN, as we did in all the big enterprises, which kept us to very important result. So my wish is that to be here in 10 years, and for the 30th anniversary of Virgo, to celebrate a new beautiful result with Virgo, and maybe to celebrate also the starting point of Einstein's telescope, and to go on in this research field. Thank you very much.
Thank you very much, Antonio. And I think that with this, we are closing the session, and there is now time if somebody want to have a visit of. Okay.
So there is one group can make the tour in English. So I invite in the first 3 row. He want to make the tour in English to follow Massimo and Gianluca on this side. E chi vuole fare invece il tour in italiano segue Diego, che non vedo, e Vincenzo, eccoci, dall'altra uscita, così. Poi gli altri partiamo.
Before leaving, I want to thank again everybody, the speakers, and happy anniversary to Virgo.